Okay, now we have the force vector. Using the forces, I can calculate accelerations, and from the accelerations I can go through the velocities and finally to positions. So let's implement that part. I want to do it this way. I want to define a step function, and in that step function I will do all that operations. So my step function will input my masses, positions, and then velocities. So I input the mass, position, and velocities of my two objects, and in my step function I calculate the new positions. Therefore, this is going to return the new positions and the new velocities. So let's have a look at this function again. My step function will input the mass, positions, and the velocities of these two objects and will return the new positions and the new velocities. So when I do a one step, that will take me from my current positions and velocities to the next positions and new velocities. And then if I do this step twice, I can then update my system and then observe its evolution in time. Okay, let's implement the step function now. Because I have my force function over there, I can use that to calculate for the first mass. That would be force on the first mass would be F1, and the unit vectors of that force would be Ux, Uy. So I calculate using the force function. Look at the parameters of the force function here, M1, M2, P1, P2. So this is the force acting on the first mass due to the second one. The second force will be the same, but of course in the opposite direction. Instead of doing all that, I will calculate the second force using my function 2. So this is going to be the second force on the second mass due to the first one and the unit vectors. Of course, I must now do M2, M1 and P2, P1. So this symmetric function will calculate the force for the second mass. Of course, these vectors will be different in general, therefore I want to do it this way. Good, with these two lines, now I calculate the force on the first and the second masses. So how I do the accelerations is, of course, the acceleration is nothing but force over the mass. So and it has to have two components, A1, AX1 and then AY1. So these are the X and Y components of the accelerations of mass 1 because of force 1. So that is going to be F1 over M1, and I need to calculate the X component of this one. I can do that simply by multiplying it with Ux1. Okay, similarly, I want to do it for the Y component, and this is going to be the Y component. And now for the second mass, these are the accelerations. F2 over M2, Ux2, F2 over M2, Uy2. Good. At this point, now I have the accelerations of both masses. I have their velocities and their positions as well. Now I can begin to do the update. Now I can begin doing the updates. So first let's update velocities. Now first begin by unpacking v1. So v1 x, v1 y. Because v1 is a tuple, I unpack it this way, so that I can work with them. Okay, I want to continue with my notation here, so I would like to call it vx1, vy1, vx2, vy2. Okay, so this is now I get the components from the tuple. Of course, now I can update the x component and the y component separately. So for the first mass, vx1 is equal to vx1 plus ax1, over there I calculated, times dt. Okay, so for a small time step, I can do this very first order approximation, where v final is v initial plus a times delta t. If I keep delta t small enough, I should have a reasonable simulation of the system. So because I have a dt over there, I can make it here dt. Let us do this, a small number, 0.01, and we can always check if that gives us a reasonable simulation later on. Okay, now before I do the vy components, I would like to write this in shorthand this way, so it gives a better it is easier to read. It shows that I am updating vx1 using the acceleration over there. So in the shorthand notation, ay1 times dt. Okay, this is of course for the first velocity components. This should be for the second one. Okay, in this way, now I have my velocities, the new velocities calculated. Because I am going to return the velocity vectors, I would like to pack them again, so that it will be easier when I return them. I always keep this, writing it the other way around, vx1, vy1, and also v2 is the components of the second vector. Good, this is the velocities update. I updated my velocity vector, components of the velocity vectors, using the acceleration components that I calculate from the forces. Good. Now I can also do update positions. Update positions. Okay, now I can begin to update my positions. So x1, y1, I unpack it from P1. And for the second point, the x coordinate and the y coordinate I obtain from the second P point, point 2. Update x1 using vx1 times dt. And then similarly for y1. Okay, so y1 is vx vy1 dt. So vx1, if I choose this one, I can see that I am calculating it in these lines, and Vy1 is of course here, there, and there. So do the same for the second point. Using the velocities of the second mass, I calculate the positions of the second mass. And last, let's use this tuples to pack as points x2, y2, and that's y1. Let's have a look at this function again. So I am returning point 1 and point 2, and v1 and v2. So from the top, let's have a look at this function. The step function uses the force function to calculate forces, and then accelerations, and then the components of the accelerations. Next, once I have the acceleration components, I update the velocities using the formula v equals v0 plus at, and then the positions from the formula x equals x0 plus vt. Okay, and then I return the new positions. Once I have the new positions and new velocities, I can always run this step function to do a simulation. Okay, let's explain this function a little bit here. This function inputs the initial positions and velocities of two masses and calculates the new positions and velocities using the force function. Okay, I think this is a reasonable explanation. And then maybe I can also do a little bit explanation here. V of t is equal to v0 plus a delta t. So this is basically the update velocity function that I am using. Similarly, for the update position function, I am using x is x0 plus v delta t. Okay, with these two remarks, I think I am done with this function. So let's save this. Now let's test this function. Okay, now I have my step function defined. So let us run this program first to see what it does. I have my dt, g, and masses defined here. I defined two positions for my objects, for my masses, and then these lines draw the masses and the curve plot for the masses. Okay, that's fine. And also here I calculate the force on M1. Let's have a look at that force. And these are the components of that force. You see they are both minus, showing that it's a negative force in the x and y directions. So let's test that a little bit. So if this is the first force, then this is going to be the second one. And then I interchange this indices here. Okay, let's calculate this. Now, okay, so this is F1 and that is F2. Of course, the magnitudes are equal. Let's have a look at the ux, uy. So this is the components of the unit vector along f1, so both negative. How about the second one? Okay, so it is the same and opposite of the first vector. Therefore, these two vectors are really the opposite of one another. Good. So I'm actually using this type of a line over there in this function here. So f1, f2, ux1, uy1, force m1, m2, p1, p2, and the symmetric here. Then I calculate the accelerations, etc. So let's take this off, and then instead let us try to do the step function p1, p2, and then v1, v2. Now, until now, I didn't use the velocities nowhere, but for this function, to calculate the positions, I need the velocities. Therefore, I need initial velocities for these two objects. Of course, the time evolution of the system depends on the initial velocities. So it's quite reasonable that I need velocities in order to run the step function. If I run it without velocities, you will see that my program will complain that I didn't define v1 and v2. So here is already an warning there, undefined name v1 and v2. So I need the initial velocities, of course. So let's define them the same way I do. v1 is, I don't really need the components here, so let me do it this way directly. So these are the initial velocities. These are the initial positions. Okay. So now can I run the step function? So let's call this next step, or the state. Let's call it the next state. Okay. Now I can do the step function and calculate the next state. Because I don't have my ux and uy available, let me delete this. Okay. So I have initial positions, initial velocities, and now I can calculate the next state. Instead of this state, I can write the positions and the velocities directly. So let's run this now. Okay, I have my two masses, and I am calculating the new positions and the new velocities. Let's see if this is indeed changing the values for the position by printing the position before and after the step function. So yes, the x and y positions are changing ever slightly after the step function. Also, I can check for the velocities if I want to do that. Yes, the velocities are also different before and after the step. So we come to a critical point where I want to show you how I do this simulation for more than one step. So let's take this print lines out. Okay, so this line is actually from in some position and velocities, calculate new positions and velocities. So I want to do this for example, 5 time steps. So inside that for loop, I am calculating the new state from the initial state. Let's run this. Yes, the function runs for 5 times, but I don't see that it is running. So how about I print the time, the step number there. So yes, it is calculating new positions for each time step. I can also have a look at the positions at each time step. So I want to do it this way. A little bit of formatting will help there. So this is the decimal formatting. This is the integer formatting, and then I have 3 decimal points for the x and 3 decimal points for the y components of the first position. So put I, the x component is p10 and the y component is p11. So this is the x1 and it is the y1. Okay, let's run this and let's see if actually my simulation is updating the positions. You can see there that the x positions and y positions are changing slowly with each time step. I can make these changes even smaller by making dt smaller. It helps to see it this way, but of course it is much better if I can do the graphics updates as well. So how do I do the graphic updates is this way. So after, when I have my P1 and P2 we are calculated, I can do my plots inside here. And so inside the loop I can draw my positions every time step. But here is x1 and y1, so I can unpack P1, x2 and y2, and I can unpick P2 over there. Okay, good. I can now I can see for 5 time steps what happens to my meshes. Of course, my velocities and positions are random, so let's run this and then begin to put some initial velocities ourselves to see how the animation works. Okay, yes, we can see that these two meshes are actually moving. Okay, I want to test my simulation now. Before I move forward, I realized that I actually mistyped x1 and this is supposed to be y1. Okay, and now to check if our physics is working right, I will want to do put my points at these points exactly. So how about we do x0 and then y 1.0. So this is the left top corner, and then my next mesh I want it to be exactly opposite. So this is going to be on the other side of my on the other corner, and initial velocities, let us have 0 initial velocities for now and see how this works. I want to run this for a short time step, and my dt I want to use a small dt over there. So I want to plot x1 y1 x2 y2. Let's run this and see how it works. Okay, it seems my dt is small and my time I am doing this for 5 steps and the points are barely moving. Okay, in that case I want to do my time step a little larger. So this is 10 times faster. Let's see if my points will be moving now. Yes, actually this is what I was expecting. For this simulation I am using equal masses and they are actually accelerating. You can see the velocities are increasing towards one another. Good. Let's see the effect of changing one of the masses. So I want to make my first mass 2, which I drove using a blue color. So I am making it a larger mass. Of course, the larger mass has slower acceleration. Let's see if this gives me the same effect. Let's write my smaller mass moved half the distance compared to the smaller mass. The larger one moves slowly. Okay, and then how about we this time move the smaller mass at the half the length in the Y position. So I would do that by moving it to this position over there. And then let's run the simulation. Okay, so when my small mass is here and the large one is over there, they again move on a line connecting one another. Okay, I am now building more confidence. And then next I want to do some initial velocities. I want my larger mass to move this way, to move horizontally. So let's give it some velocity in the x direction, and then run the simulation. Let's see. Okay, so it looks like there's a very slight change that I can see over there. So maybe this velocity is a little too small, so I make it 3 times larger. Okay, I can see that my mass is moving this way, but also curling towards the other one. So let's play with this a little further. I want to make my second mass move down, and also and give it a little bit of negative velocity on the x-axis as well. So let's see if this. That's right. So the second mass actually curls towards negative velocities, but my larger mass is actually pulling it back towards up. So how about we make the mass a little bit smaller? See what kind of an effect it is. And then I can also run this for maybe double the time step. Okay. So basically these two masses are kind of orbiting one another. To see the simulation a little better, I can now make my time scale maybe half or a quarter of that and see how it works. Okay, see the masses are actually beginning to feel one another's gravitational field. I can run this a little further. Okay, good. So I can also make my mass twice to make the other one orbited. Okay, I think I built up enough confidence that the physics is right. Let us test something. If we can create a satellite like an object around the first mass. So I want to do the first mass. I want to make it very large, 100 for example, and the second mass is 1. So because the mass is really large now, I think it's a good idea that we do the marker sizes constant, and keep in mind that now I am not making the marker points proportional. Okay, so I changed the meshes there, and let's put the first mesh at the center and the second one on the right corner, like that. And then velocities, the large mesh zero velocity, and let's for now do a zero velocity for the other one as well, and run this not for a very long time step for now. Let's see what we get. Okay, so I have my larger mass here, and the other one accelerates towards it. Okay, you may wonder why this large mass even moved that much. The reason is because our time steps allowed the small mass to really approach towards the center of the larger one, creating a lot of converting a lot of potential energy into kinetic, and that makes even the larger one work. You can think about that. So I want to do this smaller time steps, and when you run it for small time steps, you see the large one barely moves. Okay, how can I put the other one in orbit? I want to try something like this. So because when this small mass is exactly on top with respect to the y-axis, it should have only the x component. So let's move it on top of the first mass by changing the x coordinate. Let's see if it moves there. Okay, good. Um, the so the small mass, the satellite, should have a horizontal velocity component. I can make it positive x, for example. So go here and give it a little bit of velocity, and then see if it is beginning to make an orbital motion. Okay, now I can make my time steps larger. Okay, what is happening here is my satellite object is actually falling down on the larger mass. So what is wrong here? The velocity is too small for this orbit. Therefore, I can try to increase my velocity. Where is that velocity? Here. So how about I increase it to 1? Let's see the effect. Okay, I think it's small, still small, so I want to make it larger. Okay, so we are beginning to see something reasonable. I can even make it larger. Okay, this is not bad. So with that kind of velocity, I begin to make an orbital motion around. So this is 1/4 of the orbit. So if I run this for 3 times, that is nice. So I can see that my also my small mass is moving a little bit because it has 100 times the satellite. So it's not really not that big, so that it doesn't move. It moves ever slightly. So I can do this even for a larger time step to see. Yes, so I can see my second object moving in an orbit of the first one. Okay, now I will, before I let you go and play with it on changing the parameters yourself, I want to show you how I can kind of do a simple animation use on the console here. I can try something like this. Do a time sleep, for example, for 5 seconds, 0.5 seconds, and I need my time imported. For time. Okay. And then I want to see the plot every time it is updated. So I want to do a plot show here. And because it will show, then in order to have a nice figure, I want to copy this inside as well, so that for next time I again have a nice aspect ratio and X limits, etc. So let's run this and see how the simulation and how the animation unfolds. Okay, you can see the satellite-like object moving around my larger mass. Okay, good. I can stop my simulation here and then test, try something for fun. How about, okay, so dt, if I make my dt larger, this animation, the simulation will run faster. So let's see how that works. Okay. So my other object nicely goes around the first one. Okay, let's make dt smaller as it was and run this code again. Okay, good. So even in the console I can see a little simple animation. So I want to conclude this video here, and I invite you to do a proper animation using matplotlib animation so that you can see a nice smoother animation. Okay, we can discuss further about this code in the class. I hope you enjoyed it. Thank you.